All right, so now we're going to talk about the logistic equation. So logistic equation is related to exponential growth, but it's not logarithmic. It's not the inverse of exponential growth. It's a modification to exponential growth. So a lot of things appear to grow exponentially, like monetary value and population. But if population really just grew exponentially forever, then the whole world would be covered in rabbits, right? There would be infinitely many rabbits. And that just doesn't happen. So you have rabbits, that's your typical population growth. I have one rabbit. Well, I got to start with 2 rabbits, right? My 2 rabbits gives me 4 rabbits. Then my 4 rabbits gives me 16 rabbits. Then my 16 rabbits gives me, no, I can't square 16 in my head. It's not 256, is it? I guess it is 256 rabbits, and so forth, right? So it grows exponentially. But if that growth were just totally unlimited, you would eventually, the whole world would be covered with rabbits, like fairly quickly. Same with, even if you consider, for example, infection spread. So people are talking about exponential growth of COVID infections. Well, it can't really grow exponentially to an unlimited degree because there's only 7.5 billion people on the planet. All right. So once that exponential function goes over 7.5 billion, you can't have any more growth. There can't be any more infections. So what, especially in biology, is where a lot of this logistic equation came out of, is that this kind of growth has to have some kind of limit to it. And so analyzing the exponential equation in terms of its differential equation, it gives us a nice way to explain the logistic equation and how this limitation in growth occurs. So what happens is, right, this is unlimited growth. And basically, unlimited growth is really impossible. You know, you can talk about, radioactive decay is probably the most truly exponential function, although the question becomes interesting when there's only one atom of material left. And then that tail, the exponential equation, is just describing probabilities at various times. All right, but unlimited growth clearly cannot happen. Eventually, you're going to run out of resources. You're going to reach what was called the carrying capacity of the environment. All right, so the modification is to say, okay, we're going to stick with that dp dt equals kp. All right, and then so you can think that this p factor, all right, this factor says that the growth increases as the population, the rate of growth increases as the population increases. So this factor is 0 when p equals 0, and it increases, this factor increases with increasing p. All right, so what we do is we just throw in another factor, and the other factor is m minus p. All right, so m is something called carrying capacity, and it stands for maximum. It means the maximum number of things you can have. So if we come back to the simple example of rabbits in a field, let's say there can't be any more than 500 rabbits in the field, or that we just won't have enough resources. All right, so that's a maximum number of rabbits. It's called the carrying capacity. So what happens with this factor m minus p is that this factor is 0 when p equals m, equals the maximum amount. All right, and this factor decreases with p. So what this is really showing is a sort of more natural form of growth where I have one factor driving the rate of change. Remember, all this is about the rate of change, and that's the calculus-y part, and why calculus allows us to move from exponential to logistic growth. So you have one factor that drives a rate higher as the p increases, but then there's another factor that says, as the p approaches m, as the p gets closer to this maximum value, so the number of rabbits isn't going to suddenly disappear, but their rate of reproduction will cease. So what essentially means is that it's not really rate of reproduction, but they're also dying, right? So dp dt is really the birth of rabbits minus the death of rabbits. So the birth of rabbits is always increasing, but as we approach maximum capacity, then the death of rabbits starts taking over and eventually drives the rate down to 0 again. So when m equals p, you still have rabbits, but their rate of change has stopped. And so graphically what the function p looks like, it's jumping the gun a little bit, but graphically what the the graph of P looks like is like this. You start out with no rate of change, you grow exponentially, but then the rate of change starts to slow down, and you end up with, see a lot of rabbits, but their rate of change has stopped growing. They no longer have, they have a zero rate of change because they've essentially achieved an equilibrium with their environment. All right, so that's what the logistic function looks like. But we start with this differential equation, and then this is interesting if you analyze this differential equation further, because you can think of, so we're still not saying what the actual function is, right? We're talking about what the rate of change of the function looks like. So on this axis, I'm going to put dp dt. On this action, I'm not going to put time on this axis, okay? I'm going to put population. How is the rate of change affected by population? Well, if you look at this dp dt, which equals kp times m minus p, and if you distribute that out, you're going to get kpm minus kp squared. All right, so it's in terms of a function of p, so it's, you know, keeping m constant and k constant, looking at just as a function of p, all right, you have a negative quadratic. That means you have a parabola facing down. And you also know the two x-intercepts of the parabola, because the rate of change is 0 when p equals 0 and 0 when p equals m. So if I put m right here, the graph of dp dt, not the graph of the population, but the graph of the rate of change of the population, is a downward facing parabola, right? Arguably, these parts of the parabola don't make sense because the dp dt, well, I guess the dp dt could become negative. This just means we're losing rabbits, but we'll restrict the domain from 0 to m. All right, well, the population can't be less than 0, and also the population cannot be greater than m. That's why we're going to exclude these two, because they're outside the domain of p. All right, now, an interesting question becomes, when is the maximum rate of change? Well, you don't have to do calculus for that. You can just look at, in algebra 2 lens, at what is the vertex of this parabola, right? That is going to be the max dp dt, the maximum rate of change, the maximum growth of the population or whatever you're studying. All right, well, the vertex, the x-coordinate of the vertex, always falls at the midpoint of the segment joining the x-intercepts. So that's at m over 2. So you get this important idea about logistic equations, that the maximum growth occurs when p equals m over 2, and we're probably going to use that in a lot of our analysis of the logistic equation. So what it means is that if I have my population of rabbits, and let's say my maximum number of rabbits the field can support is 100, the maximum increase of rabbits will occur when there are 50 rabbits, half of the maximum available. And then all the other times it will be less. So in fact, if you look at sort of this graph, here's where we reach m as a population. Here's okay, we did like this. Here's m over 2, where we're at half the population. And you can see that the graph is steepest right there when we're at half the population. So we'll talk about that more after we do a specific example.